the random 3D option, where the particles are actually assigning themselves randomly to any old axis really. Now with restrict divergence to axis back on, this divergence is actually restricted to one axis, or a combination of three actually, using these weighting values here. So to give you an example, the divergence at the moment is 149 degrees and it's restricted just to the z-axis. So we're just limiting this particular divergence value just to the z-axis. That doesn't really give us any much of a difference really with this particular option, random horizontal. But what we could do is we could actually put that to 0 and we'll change the axis to y. And now if I put divergence on, you can see that the particles are actually tipping forwards in most cases, or backwards. So you can see now that the divergence has actually been changed to the y-axis, and this is for each particle. And you can do the same thing, you can restrict it to the x-axis, or you can use a combination of these. You could have, if I do 0.5 on one and 0.5 on another, then we've actually changed the divergence so that it can actually happen on more than one axis at once. So there you go, you can see random horizontal's got a little bit more flexibility than random 3D. Okay, let's move on to the next option, which is world space. Now in this case we'll just reset these back to their standard values. Just put this back to 1, get rid of any divergence. Now world space is more of a sort of explicit control of your particles. You can actually rotate each particle based on its x and its y and its z axis. So let's try doing that. We'll just do it with the z-axis. We'll just rotate this. And you can see all the particles are actually, pointing in the same direction. They've all got the same control there. Just put that back. You can do the same thing with the y-axis, so they tip forwards. And you can see the same thing with the x-axis, so they're just rolling on their axes there. So that's something you can do with that particular choice. Now, if I let's say do some divergence on the z-axis. If I actually rotate the particles on the z-axis, I can actually put some divergence into that again. And you can see that, again, the divergence is actually restricted to the z-axis. That's because of this option here. But as with the previous choice, again, you can change the actual axis along which the divergence can take place. You can see now they're all tipping forwards based on the y-axis. And in that way you can actually have a little bit more variety in the way your particles are oriented. But as you can see in this particular case, it's actually much more useful for explicit rotations where you want your particles to point a certain way. And then of course you can add a little bit of variety by just putting in a little bit of divergence on whatever combination of axes that you want to use here. The next option is speed space. So we'll just do this, and again we'll reset these back to these different options here. There we go, just put those back. Now in this case we'll see the particles get emitted and they're traveling along the direction of travel that they're actually emitted on. So I'll just move this over here so we can see a little bit more clearly. Out come the particles and they're traveling in that, and you can see as they're created they're actually all heading off in the direction of travel. But as the animation progresses, you can see they're not continuing to keep that relationship to the direction of travel. So if I just put them out to here, you can see that with speed space you've got a bit of a combination of this and the previous with world space. You can actually veer the particles off the originally assigned rotation value just by changing these x, y and z parameters. And again, as is pretty common with a rotation operator, you can put some divergence in there to give them a little bit of randomness. And again, you can restrict that to whatever axis that you want to. So you can see this is basically a one-off rotation assignment, which happens as the particles enter the event. So this is useful when you want to orient your particles in the direction of travel just once, and then from then on you want to do something different. So that's what this particular option is used for. Now a very useful option is the last option, which is speed space follow. So I'll just turn on that option, and again you can vary this one based on the three different axes. You can actually custom control exactly the orientation of the particles, which is an offset of the actual speed space follow function. What that function actually does is, as I said earlier, it's actually fully dynamic. So scrub back to the beginning, and out come the particles, and you can see that they're facing the direction of travel. Now, as the direction of travel changes, you know, as they start to orbit around this force here, this gravity force, the rotation of the particles is updated to respect that orientation. So you can see that as the particles fly out, they are changing direction. So, and if you look at this particular particle here, you can see he kind of turns a corner as he slows down. He rotates around and he's heading back towards the force. And you can see that's happening for all the particles. So if I scroll that out to there, as I just said, you can actually, you know, control these a little bit. You can actually tip them off their axes if you want to. Just put that back. You know, do that with the X, Y, and Z axis. So you've got some pretty cool control there for actually controlling your particle rotation. So that's it for this particular operator. What we'll do is next we'll move on to the spin operator. We won't actually move on to the scale operator. We'll actually move on to the spin operator. And the thing about the spin operator is it's actually a kind of rotation operator. So it actually makes sense that we move on to that before we move on to scale. So let's do that now.